Um, Today, the main topic for today is we will continue our discussion about the equilibrium. So, there are several problems. I believe just now you told me that you are still having a problem, and this is one of those. Matthew, which not just Matthew, but the rest as well, the rest of the student as well. Which part of this problem that you are still having a problem? Hello, Matthew.
For me,
Mhm.
it's trying to understand that the weight at the weight 1,800 millimeters away from A is 1,100
Okay.
Newton instead of just 800.
No, no, no. I'm not saying that the weight will be 800. Sorry, not saying that the weight will be 800 plus 300. So it's supposed to be 1,100, right? I'm not saying that the weight will be 1,100, but I'm saying that the normal force, okay, that the normal force which is withstand by the beam will be 1,100. So basically, this is please try to listen carefully to what my explanation right now, because this is very important for the free body diagram and the equilibrium. Okay, because separating the system into several free body diagram is slow, and sometimes we cannot just see the system as one system only, like that. Okay, so basically we can see the system into several. We can see the system as a uh, in several ways. I will I will show it to you one by one. So I will just show it to you, not just how to solve it. I will not show you how to solve it, but I will show you how to draw the free body diagram to solve this particular system. Okay, the first option. Ella, why it's like this? Okay, okay. The first option. Okay, the first option is the whole system. Mm, yep. The first option is the whole system. We can do it this way. Okay. If I want to do that, this is the free body diagram that I will draw. Okay. When we draw the free body diagram, remember all the weight must be there. All the external forces must be there. Correct or not? So whenever we draw a system, whenever we draw a free body diagram, we have to put all the external forces plus the weight of the system. Correct or not? Hello, answer me. I'm not Rashid because I've seen
Yes,
you
sir.
lying down, so I will just keep asking you. Okay, Hamad Rashid.
Yes, sir.
Okay, yeah. Uh, Correct or not? We supposed to draw all the external forces plus the weight which is happening at the system. Correct or not? That's the
Yes.
point of free body diagram. So draw all the external forces and the weight as well. Okay, the gravitational force, and the external forces. That's the whole thing that we're supposed to draw. So basically, at A there will be a normal. There will be AX, AY, and moment because it's well defined, right? Okay, moment at A. That's at A. Okay. Then please ignore the line there. Okay. Then at B. Sorry, not at B. At G. What will be happening at G there? Ahmad Rashid. external forces that are happening at? What kind of forces that are happening at G?
G ada gaya yang ke bawah, sir.
From this one. Okay.
From
the weight of the steel beam. So it's supposed to be 2000 Newton downwards. Yeah, because I'm using G equal to 10. Okay. And normally you're supposed to use G equal to 9.81 meter per second square. But for this one, in order to make it fast, I use that. Okay. Then, beside that, we have another weight, right? The weight of the man, correct, right? The weight of the man is 80 kilograms times 10, so 800 here. Okay, what are the external forces? What are the external forces and gravitational forces which is happening at that particular system? Anyone here?
The load from the man.
The load from the man, 800 Newton, right?
The force.
The 300 Newton pull.
Remember, you can see here, this is the system that we are drawing. So the load of the man in this particular system become internal force, and we ignore that. We always ignore internal force whenever we talk about equilibrium in one free body diagram. We consider it as internal force because it's not external force, and because it's not external forces. What I mean by external force is the force which is happening outside of the system. Okay, the force which is happening in the system because of outside force. Outside force there is a part which is not a part of the system. Okay, so the force comes from other part beside the part that is inside of the system. So that's why the welded pin there, because I limit the discussion on the beam, man, and the pulley system. There, the beam there, okay, the beam there, the pin there is not part of the system. The beam is part of the system. The pin is not part of the system. That's why AX and AY is there. MA is there. Okay. In this particular free body diagram, we're supposed to draw it like this. Only from this. And the force is supposed to be 300 newtons times 2. Why 300 newton times 2? Because if we draw the free body diagram of the pulley, it will be like this one. 300 Newton, 300 Newton, and the one going down is 600 Newton. Correct, right? So this one is 600 Newton. This one is 600 Newton. So you can draw the system like this. This is the first way of drawing the system. But maybe some of you asking me, sir, if I just want to see the beam only, can we do that or not? The answer is you can. So if the next one is I want to just see the beam here as my system, only the beam as my system, then you can. This is the second way of doing it. Only the beam. If it's only the beam, outside of the beam will be external force. And we have the weight as well. The weight of the beam from gravitational force. Any other things besides the beam become external force. AX and AY is still external force. MA is still external force. Okay. What else there? How about the contact between the man and the beam? Will there be any force there? Ahmad Rashid, will there be any force there?
Yes.
The contact between the man and the beam, will there be any force there?
Gimana sir? Kurang ngerti.
Kontak antara orang sama si beamnya itu akan ada gaya atau tidak? Kan ini kan saya meninjau si beamnya.
Ada sir.
Besar gayanya berapa?
Besar gayanya 800 ke bawah sama 600.
600? Enggak dong kok 600. Kita coba harus... Okay, in order to answer that, you have to draw the free body diagram of the man.
Oh.
This is the free body diagram of the man. Okay. Okay. If you see this, the man has a weight of 800 newtons, right? Going down. The weight is 800 newtons. What else is happening on the man? Ahmad Rashid. He's pulling upward.
Gimana sih?
Apa hal gaya-gaya apa lagi yang terjadi pada orang? Dia menarik.
Ya, menarik ke bawah.
Menarik, kalau menarik ya ke atas dong. Dia nariknya ke atas.
Okay. Gayanya ke bawah berarti.
Dia narik ke atas, oleh karena itu dia akan tertarik ke bawah. Besarnya berapa?
Ya. 300
newton. Apalagi yang terjadi di sana?
Ada gaya lagi dari tarikan itu. Dari katrol ke atas.
Enggak ada itu. Ini, apakah ada orang itu ada mendapatkan gaya normal dari beamnya tidak? Kalau enggak kan dia berarti percepatan ke bawah dong.
Oh iya. Gaya normal, 300 juga, sir.
No, you cannot answer it that way. This is the normal force. The normal force is supposed to be makes all the things here in balance condition. That's why it's supposed to follow sigma Fy equal to 0. That's why based on this, you will have n minus 800 minus 300 equal to 0. Which means your normal force N will be equal to 1,100 Newton. You get it? Ahmad Rashid.
Yes, sir.
1,100 Newton. Where are we supposed to put it? Yeah, in the middle, like this. So, in the middle of the person like that. So, this one is 1,100 Newton. What else? So we have that, which is happening on the beam. Ahmad Rashid. How about from the pulley at the bottom?
Nggak ada, sir.
No, there is, yeah. Because remember, the system that I'm talking about, okay, the system that I'm talking about is just the beam. So anything outside the beam is supposed to consider as external force. So there, supposed to be tension force there, going down 300 newtons. You get it, Ahmad Rashid?
Oh yeah, yes, sir, yes.
Yeah, Matthew?
Sir, I have a question. Is the normal force of the man considered as internal force of the beam?
Normal force of the man, which one? In the first system or the second system?
The first system.
The first system, yes.
The second system, sorry.
The second system, no, it's part
Just
of the external force.
So only the weight is considered as the external force?
No. The weight of the beam, no, the internal force.
Oh, sorry. I mean the weight of the man plus 300.
Yes, it becomes external force for the beam, like this way.
So the normal force is exerted by the beam, yeah. That's why it's called the internal force?
No. The normal force is action-reaction with the weight and the pulling force, this one. And the normal force here, because it's action and reaction, the normal force is going up for the man here, but it will be going down for the beam, right? Because it's action and reaction. There. So what happening
Alright.
here is supposed to be action and reaction. So the man is getting 1,100 up by the beam. The beam is getting 1,100 newtons down by the man. You get it? That's why I draw it this way. Even though here N is going up, but here N is supposed to be going down. Why N is going down here? Here, why is N going down? Because it's action and reaction. You get it, Matthew?
Yes, sir, I do. Thank you.
But if you take a look here, the first system and the second system is exactly the same. It will produce exactly the same results. So you can see the system, you can divide the system as much as you do, as long as it can solve the problem. So you can view the system differently. That's the thing. Drawing a free body diagram is an art. Actually, it's not an art, it's a logical. Okay? You can see the system differently. You can consider the man and the pulley as part of the system. You can consider only the man as part of the system. You can consider only the beam as part of the system. It's okay as well. So there are a lot of ways to draw the free body diagram, but either way, system 1 or system 2 or system 3, maybe if you can find, actually I can find another one, but I don't want to discuss it here as well. System 1, system 2, and system 3, or any kind of system that you can create, as long as you do it properly, okay? The result will be exactly the same. Okay? The result will be exactly
So, sir, the result will be exactly the same. We can we can use diagram 1 or diagram 2.
Yes, correct. So moment at A, AY, AX for diagram 1, free body diagram 1, and free body diagram 2, the results will be exactly the same. But of course, here you have to complete it with the correct dimension. Okay, here the distance here is supposed to be 300, right? But here the distance here is supposed to be 150. Why 150? Because 600 is happening exactly in the middle here at this particular point. So that kind of detail is supposed to be there as well. But I didn't complete this free body diagram with the dimension. Do you get it, man?
But for the first diagram, what happens to the tension of the rope, sir?
The first diagram, the tension of the rope becomes the tension of the rope here. This one and this one. Huh?
Yes, that one.
Yeah, it becomes interforce because it's part of the system. The tension of the rope, which is not part of the system, is just this one. That's why it becomes external force. This 600 Newton. You get it?
Can you?
Whenever the tension of this, the tension here, and the tension here is part of the external. It's part of the internal force. Whenever it's becoming internal force, you don't have to consider that. You don't have to consider that in your free body diagram. We never consider internal force in the free body diagram. Why it's internal force? Because I draw the system, right? It's part, right? It's part of the system, right? This one. Correct, right? So it's inside of the system. Correct or not, Matthew?
Oh, I see.
It's inside of the system. So that's why it becomes internal force. Whenever it's inside of the system, if it's not external, whenever you draw a free body diagram, if it's external force, yes, you have to draw it. If it's the gravitational force, yes, you have to draw it. You only have to draw two kinds of force in your system. External force and gravitational force. If it's not part of those, for example, internal force, it's forbidden for you to throw it. You can't throw it. You cannot throw it because it's part of the system. Why you have to throw it? It's part of the system. But when you take a look at the second system, yeah, because the man is not part of the system, the bottom bully is not part of the system as well. Okay, then it becomes external force. Do you get it, Matthew?
Yes, thank you, sir.
So one thing that you have to remember, okay, one thing that you have to remember is there are two kind of force. Yeah, there are two kind of force which you're supposed to which you're supposed to include in the free body diagram. The first one is the external force. The second one is the gravitational force. Okay, only those two forces that you're supposed to include in the free body diagram. Okay, I believe it's supposed to be clear enough, right?
Sir, I want to ask in the problem before.
Okay.
In there, it is 600, right, from the center of the beam. And in the kan ada kayak gap gitu ya, sir, di katrol. Nah, itu berapa milimeter, sir?
Gap di katrol untuk yang tadi yang sistem pertama atau yang sistem kedua?
Bukan. Jadi saya udah ngerti yang tadi force-nya itu. Yang saya bingung itu ini kan ada 600, tapi kan di tengah-tengahnya kayak bolong gitu kan, di tengah-tengah katrolnya. Nah, itu berapa milimeternya tahunya dari mana ya?
Di sini maksudnya?
Bukan.
Ini?
Ya, that.
Ini loh, dimensi ini tuh artinya 300 mm itu artinya gapnya itu.
Gap ke ujung berarti itu 300 meter.
Jadi,
itu milimeter.
300 mm ini loh, coba lihat.
Diameter katrolnya 300 jar.
Ya, betul. Itu saat kita, ini kamu tuh gambar tekniknya itu, kamu harus dengerin kuliahnya itu ya. Nih, kalau artinya gini, itu boleh 300 mm itu boleh, itu ditunjukkan gitu, tapi boleh juga ditunjukkannya seperti ini. 300. Itu artinya adalah si tebalnya 300, si ini 300, jaraknya itu 300. Bisa juga ditulisnya kayak gini, 300.
Oke.
Kamu nggak dengerin kuliah gambar mesin ya? Ini gambar teknik ya?
Nggak tahu deh, kayaknya ini saya belum masuk juga deh, saya juga nggak tahu. Kayaknya
nggak dengerin.
Belum ada, sir.
Belum ada.
Belum ada. Oke, langsung di backup sama temennya. Oke deh. In that case, if it's not yet given, the meaning is like that. Okay, it can be like this. You can show it this way, or it can be like this as well. So you get it, right? If it's like that.
Yes. Okay.
Because just now, okay.
Okay, thank you, sir.
Yeah, no problem. Okay, I think we'll
sir.
start with this. Yep.
Also, why yang the rope connecting the pulley to the ground is restricted from the system? Kenapa sir pilihnya only until katrolnya yang jadi sistemnya?
Kalau misalkan sebenarnya kalau mau ditulis juga nggak ada masalah sampai ke bawah ini. Maksudnya yang untuk sistem pertama kan?
Ke tanah gitu nggak bisa ya?
Boleh. Kalau mau boleh.
Iya,
ya.
Kayak gitu.
Cuman kan tetap aja di sini itu kan pasti akan ada gaya reaksi kan? Dari tanah ke si tali di sini pasti akan ada gaya reaksi kan? Gaya reaksinya sama aja dengan tali ya dong.
Oh iya.
Benar nggak? Itu.
Iya.
Sir, yang coretan tadi yang ada 1100 di
Kenapa
atas.
kalian pada nanya pakai bahasa Indonesia sih?
I'm afraid like some of the friends do not like fully understand, sir. So may I see like the doodle before, the one where you have 800 and 600 and also the 1100 and the 300?
I lose it because just now I used the different annotation. But what things that you want to ask?
The one in that you made it 800 and 600. That's the approach of the external force, right?
800 and 600. Why 600?
Like between the man and the pulley.
Yes.
And so the 1100 and the 300. That's the.
Okay. So actually, there are several ways to take a look at this problem. So whenever I just take a look at the beam as the system that I consider, apart from the gravitational force which is happening at the beam, okay, yeah, this one, everything else are external force, correct? Correct or not? Answer me.
Correct, sir.
Yeah, betul. Okay. Everything else is external force, including AX, AY, and moment at A. Okay. What else is there? Remember here, there is a connection, right, between the rope and the beam, right?
Yes.
So there's supposed to be external force as well. 300, right?
Yes.
And beside that, here, actually the rope is not touching the beam, so we don't have to consider as external force there. But remember, here the shoes of the man is touching the beam, correct or not?
Correct.
So it becomes the normal force there. In order to know the whole normal force which the man gives to the beam, I have to draw the free body diagram of the man first, correct or not?
Correct.
Yeah. So this is the free body diagram of the man. Okay, so this will be the normal force that we are talking about. If we take a look at the man, the normal force is supposed to be going up, right?
Correct.
But here, the normal force is supposed to be going down because it's action and reaction, right?
Yes.
Okay, and in order to know the value of the normal force, I have to know whatever forces which is happening at the free body diagram of the man, right?
Yeah.
The man has weight of 80 kilograms, so 800 kilograms. What else is there? The man is pulling the rope, right?
Right.
Pulling the rope up means he get pulled by the rope down, right?
Yes.
So 300 kilograms down. That's it. This is the free body diagram of the man.
Also, the pulling action becomes of the normal force.
In total, yes, but you cannot say it that way directly because it's not direct, right? So 800 plus 300 will become the normal force, and that the normal force here is the one that will be considered in the system 1100. Do you get it?
Oh, so it's the man and the pulling action becomes the normal force, and
yeah,
also
the normal force here. Yeah, the normal force here is the one that we're supposed to consider here. I don't care about the pulling action in this particular free body diagram. What I care about is what happened here at the shoes of the man when the shoes of the man touching the beam. Do you get it?
Oh, I see. Sir, if the other end of the rope doesn't touch the beam, does the pulling action become part of the normal force like in here?
If what?
If the other end of the pulley is not connected to the beam, does it come into this calculation?
It's still
jatuh dong talinya.
Still, no. I mean, no. I understand what you mean. Okay, the other end here is affect this force. Okay, but if the other end here is not here, not touching here, but for example, the rope is going straight like this. Okay, the rope is going straight like this. There is nothing like this, nothing like this. Okay, the 300 there will be gone, right? That's all. But 1,100 is still there.
Oh, I see.
Do you get it? Right? Because 1,100 is coming from the normal force here. Okay?
Oh, okay, sir.
Yeah. So you have to take a look whenever you draw a free body diagram. You have to take a look each point where there is a connection between the external part with the system. So for just now, okay, there is a welded pin here. That's one. Then the normal force between the shoes. That's two. And this one, the connection between the rope. That's three. And beside that, plus gravitational force. Okay, that's the thing that you're supposed to do. You get it?
Oh, yes, sir.
Good. Okay, let me check with my assistant whether he's ready or not. Okay, yeah. He said that everything is ready by 11:30. Okay. So we will finish the class strict at 11:25. So you will have time, 5 minutes time to prepare for the quiz. Okay. I will continue then. This one, this one, if you want to practice with it, it is okay as well. Try to practice with it. Try to practice with more problem. Okay, because in statics, practice makes perfect. Okay, maybe some of the problem here that we haven't discussed yet, I will include it. I will include it in the next homework. The next homework I will publish it by tomorrow 9 a.m. Okay, not tomorrow at 9 a.m. Tomorrow, maybe tomorrow after. Okay? There are several problems here which actually you can try it by yourself, right? Some of those are quite interesting. Some of those just are normal, like this as well. Like this, it's not that hard. It's just normal. Okay, this one as well. This one as well. Actually, there are a lot of problems here you can try to practice with. Okay. Where is my okay. Number one is supposed to be okay, right? Number two is supposed to be okay as well. Then let's go to number three. What's wrong with number two? Hello. Who said that number three is difficult?
Sir, I'm not sure on how we should approach it.
Fatah Banyunuki Rasikin. Oh, this is supposed to be you, right? Okay. Why I cannot copy and paste it? Yeah. Copy. Okay. How should we solve this particular problem? Just now who said that? Asif. What do you think, Asif?
I think we can first and foremost like identify the forces in there, I mean, I get the first, but for the second part, I'm not so sure.
Okay, I believe most of you are getting the results for the first one, right? Because the right angle, the mass m, so the whole mass is m. So okay, the friction at the pivot O is neglected. Okay, determine the magnitude of the normal force at A and the magnitude of the pin reaction at O. Okay, so basically, the total mass is m. If the total mass is m, 1/3 of the m will be here, 1/3 of the m will be here. Sorry, 2/3 of the m will be there. Correct or not?
Correct.
That's it. Yeah, 1/3 of the m, the COG will be here. The center of gravity will be there. Correct or not?
Correct.
And the 2/3 of the m, the COG, the center of gravity will be here.
Yes.
Okay, and based on that, I believe you will be able to get the normal force at A and the reaction force at O based on those data. So the free body diagram is supposed to be as simple as this. Okay, the O there is supposed to be OY, OX, and here there's supposed to be AX. And then we have a gravitational force as usual. Remember, whenever we draw a free body diagram, you're supposed to isolate the system. The system that I want to isolate is only the L beam, the L beam only. So that system will become my free body diagram. Everything else will become external force. So AX will become external force, or X or Y will become external force, right?
Yes.
And remember, you cannot draw the pin O anymore. So in your free body diagram, it's supposed to be free of pin and free of the fixed connection, free of the rotor as well. So you only draw the body. Okay, then what else do you have to draw? The gravitational force. Here, there is a gravitational force going downwards. Here, there is a gravitational force going downwards. What is the value there?
The left-hand side is 2/3 of the mass times gravity, so 2/3 of the
m
force
multiplied by gravity, right?
Yes.
And this one is 1/3 m multiplied by gravity, like that, right?
Yes.
Okay. So later you will be able, because all the dimension is complete and the angle there is complete as well. This one is 30 degrees. Okay. The angle there is complete. So basically, you will be able to find out the AX, OX, OY using this, right? And sigma X equal to 0 and sigma moment equal to A. Correct, right?
Correct.
Three equation, three unknowns. What are the unknowns for X, Y, X? We're supposed to be able to solve it, right?
Right.
So the first one is not supposed to be having a problem. Right? The second one, what is the problem?
I'm not sure if we have to do like double the, whether we use like only the normal force, or do we combine it with as a resultant with the ones acting on O?
Okay. Now, I'm asking you here, Azad, what is the second condition that we have to fulfill?
Sir, does that mean there's no
loss
normal force at A?
Who said this? Matthew.
Yes.
Correct, Matthew. That's it, Azad. So, Azad, okay, this one. Lost contact at A. The meaning of lost contact at A means there will be no contact at A. When there is no contact at A, what will be happening there? Azad?
The normal force will be overcome with the wait.
Yeah, in the free body diagram, what will be happening in the free body diagram? Will AX will be AX, there? Will still be there or not?
AX will be gone.
AX will be gone. Yes, correct. AX will be gone. So your new free body diagram will be like this. Okay, everything else is still the same. This one, but AX will not be there anymore. OX will still be there. Okay, OY and OX will still be there. But there is one additional thing that will be there, right? From here. Correct or not?
Correct.
Yeah. So the tension force here at this particular point will be what? If you cannot answer it directly, you have to draw the free body diagram. Okay, this one is M1 multiplied by G, and there will be T1, T2. Using sigma moment, T1 will be equal to T2. Then using sigma Fy, what we will have is 2T1 equal to M1 multiplied by G. So T1 is equal to M1 multiplied by G divided by 2. Correct, right?
Correct.
Yeah. So here, this is what we will have there. M1 multiplied by G divided by 2. Okay?
Yes.
This is the condition. And the unknowns there will be OX, OY, and M1. Right?
Right.
Will you be able to get M1? Hello, Asaf. Will you be able to get M1? Now the unknowns are still free, right?
Yes.
So you will be able to get M1 because we have sigma Fx equal to 0, sigma Fy equal to 0, and sigma moment equal to 0. And if the question is just M1, actually one equation is enough, which is sigma moment at point O. Using sigma moment at point O, you will be able to get M1 directly. You get it, Asad?
I think I can't really put the pieces together. So with the sigma moment at 0.
Sigma moment at O, yes. Sigma moment at O. Yeah, sigma moment at O, OX and OY will be gone there. So the variables that will still be there will be M1. So you will be able to get M1 directly. You can try. Okay, you can try sigma moment at O equal to 0. You get it, Asad?
Yes.
Okay. Anyone else want to ask a question about this problem? Anyone else? Or it's clear enough? Supposed to be clear enough, right? Okay, next one. Number 4. What's so hard about number 4?
Actually, sir, now that you have explained yang pertama itu, actually I have more grasp about this one.
Yes. So actually, for number 4, as long as you understand completely on how to choose the correct free body diagram, the correct system that's supposed to be drawn in the free body diagram, okay, it can be solved. But remember, for this one, it's not as easy as our first problem today, because for this one, only one free body diagram which can solve this particular problem. So there is no option. For the problem number 1, the previous problem, the first problem that we discussed today, there are several ways to solve it. there are several free body diagram options that can be used. But for this one, it's only one free body diagram. Okay, it's only one free body diagram.
Sir, is it because the angle between the guy pulling and the beam is not shown?
The angle, yes, correct. That's why that's one as well. Plus this one, the contact force there is we are not sure about that. Right? Okay, the normal force there, the friction force, there is a normal and friction force here as well. So there is no data on that. Huh? That I think there is no data on that. That's why we have to choose correct free body diagram to solve this particular problem. And because I already told you that this is your homework, and I believe that most of you having a problem with this. I'm sorry that I'm moving around because there are a lot of mosquitoes in my house. Okay. Then I will tell you how to draw it. What is the correct free body diagram? So basically, the problem here is we don't know about the angle of the pulling here. The theta here is not known. So we don't know the theta there. So in order to do that, try to make sure that things become internal force. Okay, that thing become internal force. If you can make sure that thing become internal force, you solve most of the problem. So this is how can we solve this? So basically, the system that I will try to take a look at is this. Okay, outside of that, it becomes external force. So the holding now, the inside of this, the inside of that will become internal force. The outside of that will become external force. Plus, you have to consider about all the weight as well. So now, uniform 200-pound force beam. So the beam exactly in the middle, it has a weight of gravitational force of 200 lbf, right? That's the weight of the beam. Then the buoy itself has 120 lbf. Yeah, right? 120 lbf. The weight of the ball. Okay, what else then? What are the external forces there? That's the two weight or the gravitational force that we have. Only those two. What are the rest of the external forces there?
The pulley maybe in the below, sir. The 2-inch one.
Yeah, it's becoming
the rope holding the pulley, sir.
Yep. So actually, just one going down, and the force is supposed to be
80 maybe.
Not 80. The force of the buoy exert a pull of 40 lb. 40. Beside that, here, the other point here, there is not a pull there, right? Yeah, sorry, maybe slightly here. There is not a pull there.
Yes, sir.
40 lbf. It's the first one here. comes from this. The second one comes from this rope. The first one comes from this rope, and the second one comes from this rope. So we have 240 lbf there. Beside that, we have at A there will be AY, and at O there will be OX and OY. So that's it. That's the free body diagram, and all the dimensions supposed to be completed. You get it, Mati?
Yes.
So it's just how can you choose the correct free body diagram? How can you choose how to choose the correct system to be drawn in the free body diagram?
Sir, is this fine because the rope is not perpendicular to the ground?
The rope is not perpendicular to the ground. Which one?
At the bottom of the pulley. Oh, never mind.
Yeah, I don't care about that because I cut the system here.
Yeah,
so what I only consider is the tension force here at this particular rope and tension force here as well. I don't care about the bottom one.
Why is it downwards, sir?
Why downwards? What do you think?
Because we're seeing through the beam.
Yes, yeah. So if we take a look at the pulley force, right? The pulley force will be like this. And this one will be 40 and 40 lbf. Okay, this part, right? This tension force is considered as internal force, right? But this one is considered as an external force. That's why it's going downwards. Correct, Matthew?
Yes.
That's it. Actually. Okay. Anyway, it's because it's already 10, almost 10:25. I think I have to end the class. Okay, because you have to prepare for the quiz. The quiz will be start sharp at 11:30 sharp. So please check the MS Team. Everything is set automatically by Kak Rifki. Okay, so you can try to solve the problem in 50 minutes and then submit it. Okay, the problem is not that hard.
Sir, I want to ask one more, just a simple question.
Okay.
Do we need to resultant the fx and fy of O, or just state that fox is equals to blah 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 and foy is equals to
ox equal to what and y equal to what? So you don't have to add it. You don't have to sum it up.
Okay. Thank you, Pak.
I think that's enough for today's class. Please start preparing for the quiz, and by 11:30 the quiz will start, and you have to submit everything by 11:45. So the problem is simple, so you don't have to worry about it. Okay. Thank you very much for listening. See you guys tomorrow morning. Okay, tomorrow morning we will start discussing about class. Okay, see you guys. All the best for the quiz.
Thank you,
Thank you, sir.
Thank you,
Thank you,
sir.
Okay, bye bye.
Thank you, sir.